I finished this problem yet, did I? The problem where we had this ramp force acting. How far did I go? Did we finish derive the equation?
We got here too.
Okay. So I did derive the displacement response. Let me look at yours. Okay, perfect. Okay. Before I continue that, let me just say a few words again about Duhamel integral, because I don't want to see that doing this problem in particular, which intentionally I'm going through all the detailed derivation, be perceived as sort of a mathematical practice. So let me point out this. When we've been talking about, obviously, forced vibration, okay? And mainly what we have discussed up until now when that introduced Duhamel integral was basically we had a harmonic force acting on the system, right? Let's not forget the main objective of vibration, studying vibration, is what? We want to eventually not just derive the displacement response as a function of time, but the ultimate goal is that we want to find under a dynamic load what is the maximum displacement that results from the action of that force, which will help us obviously to find the maximum stresses and so on for the design application, right? In case of harmonic force, no matter how complicated that harmonic force is, even if it is periodic and whatnot, we saw that basically the maximum, evaluating the maximum displacement was not really that difficult. It came down to basically if having the static displacement times the maximum value of the frequency response function. So no matter what the frequency of that forcing function is, the amplitude, whatnot, we know that we have a relatively straightforward way to find the maximum displacement. And that's what, in case of general loading, is quite different from harmonic loadings. In other words, we do not have such a straightforward approach. We're going to get to that. We will see that when we talk about the response spectrum. But the point is that in a case of a general loading, we need to find that time response not just in one given specific type of loading, but during the regions of those loads, which may be something like this, for instance, more than 2 regions, right? What is the force? What is the response here? What is the response here? What is the response here? And then we need to evaluate when that maximum displacement is going to happen, and we cannot do it this way. The only way we can do it is by taking the derivative of the function that, for instance, we derive here, equate that to 0, find the time that corresponds to that basically maximum value, and see if that displacement that we get here is really the absolute maximum, or the displacement that we get here is the absolute maximum, and so on. That's what makes Duhamel integral more involved, and this whole operation much more, I would say, extensive than what we've been doing with harmonic force. So what I'm going to do, I'm going to finish this example problem so that we can get at least a taste that finding the displacement response itself is involved, depending on how many, for instance, sections or segments this force has. But the next step would be to find the maximum displacement. So with all that introduction said, let me finish this problem then. So for the first part, we concluded that we got a displacement response that was like this. So for this case, okay, this was TD, the forcing function. Now if I call this region 1, that means from here all the way to here, and this is region 2. For region 1, U using Duhamel integral was 1 over m omega n, integral from 0 to t of f of tau, which in this case was f0 times 1 minus tau over t d times sine omega n t minus tau d tau. And we saw how using integration by part and so on, this resulted in a function like this, t over td plus 1 over omega n td, okay, sine omega n t minus cosine omega n t, right? So this is what we derived last time, right? So this is the response of this system while this force is acting on the system. In other words, from here all the way before reaching that point. When we get to that point, we know, of course, what the value of the response would be by just substituting t is equal to td in this function, right? But in general, that is the response. And if I want to know when this would be maximum, I have to take the derivative, equate that to 0. That will give me a time which corresponds to that maximum value. Put it back into this equation to find the maximum displacement, right? Now for the second portion now, what is happening? For the second portion, you can look at it in two different ways. One is that obviously, as you can see from here on, you have no force acting on the system. And the system is undamped. So you have a free vibration of an undamped system that is induced by some initial conditions. Those initial conditions are that at this point you have a displacement and a velocity value that you find by substituting t is equal to td into here. That'll give you that u. Take the derivative, substitute for t is equal to td, gives you the velocity here. So in order to find the response from this point on, you just look at the expression we had for the free vibration of undamped system due to initial conditions, where these are the initial conditions, right? Another approach would be, you can just write this. You can say that u of t would be what? Would be the response evaluated using Duhamel integral from 0 to td of f0, 1 minus t, tau over td, okay? Sine of t minus tau d tau. So you evaluate this up to this point now. The complete displacement up to that point, plus, okay, the 1 over m omega n integral from td to any time t after that of f tau sine omega n t minus tau d tau. Obviously, this is 0 after that td. So this integral is useless, right? So the response then would be just simply this. In other words, if you basically do this integration, what would result, it would be exactly the same as if you had evaluated these two initial conditions and written the free response due to those initial conditions. Either way, what you see that if you do that, perform that operation, you end up with something like this. I don't go through the details of that, but again, as you can see, sine of t would be constant coming out, so you have to expand this, integration by parts, and so on. If you do that, you end up with something like this. Sine omega n t times 1 minus, I'm sorry, no, just minus 1 over omega n td cosine omega n td plus 1 over omega n td, okay, minus cosine omega n t times 1 minus 1 over omega n td sine omega n td. So this is the response for when t is greater than td. So,
curly brackets will be in the end.
I'm sorry?
The curly bracket's supposed to be in the end.
Oh, sorry, yes. So as you can see, as I said before, when you have a forcing function in general form, for each period that force changes, you need to evaluate a new response function, okay? And obviously, needless to say, this is not an easy process, right? For that reason, I sent you actually an email this morning. I don't know how many of you have had a chance to look at it. The response of a typical single degree of freedom undamped system under the action of a wide range of typical forcing functions, like the impact load, impulse load, half sine load, ramp loading, a large number, about I guess like 20 most common types of loads have been done. As you can imagine, each of them has involved pages and pages of integration, and the responses for these cases, in other words, for each region of the loading, has been tabulated. So you don't have to really, at least for those most common cases of general loading, you don't have to go through the pain of evaluating all that. So that's the good news. But the bad news, or not so good news, is that you still, given these functions, in contrast with the harmonic function, you do not know, for instance, is the maximum displacement going to happen here or here? In other words, is this function's maximum value smaller or larger than this one? That's what you have to do. And there's no choice but taking the derivative, equate that to 0 for each of these two cases, substitute it back into that equation, find the u, see which one is larger. And that's the maximum value, okay? I will try to demonstrate that through at least a practical case so you can see the application of that. But let me repeat myself that at least for the most common types of loading, these are tabulated. So at least you do not have to derive the response functions. We will also introduce another approach, which is actually the most practical approach, because I'm sure you're going to say, what happens if you have something other than those 20 cases? Then we have to basically use numerical integration. We'll talk about that later. But before doing that, let me do a more practical example and at least demonstrate how we can find the maximum value of the displacement in case of a nice or typical sort of a general loading. And I'm going to do this example, okay? Let's say you have a simple structure, maybe a water tower, carries about 100,000 pounds of water. The stiffness of the column is given. K is 3 times 10 to the 5 pound per inch. This water tower, of course, in California, I'm sure that's not news to us, is subjected to a blast loading, or maybe some kind of a pseudo earthquake loading, you know, depending how you look at it, which is like this. Very short duration, a load that has a suddenly gets to a very large value and then drops, okay? Which we assume that even this is symmetric. So this is, let's call this T0, and this is a very short duration loading. That's why we call this a blast loading. So it's about 0.016 second, 16 thousandths of a second, right? We want to find out what is the maximum displacement of this water tower. We need to find out because we don't know whether the maximum force displacement would happen while we're here, or here, or here. We have 3 regions for which we need to evaluate this Duhamel integral. Okay? This is done in practice when you design buildings or structures, especially in case of structures. You think of the worst, so you actually subject them to both computationally, sometimes experimentally, to some real heavy-duty, severe cases of loading. In fact, you don't have to go that far. I'm sure many of you have traveled over the new Bay Bridge. It's not new anymore, it's a couple of years old, right? Connecting Oakland to San Francisco, which is the first bridge in the world that when they were designing it, designing the deck of the bridge, they subjected that to, and it's a relatively large deck. They tested it, I think it was somewhere in the, maybe Mojave Desert or wherever it was. They took actually a real full span, they built it, and they put a car, large car, filled with all kinds of heavy-duty explosives and tested it to make sure that deck does not basically fail. So it is designed for, it's a very interesting project. It took quite a few years to build it, and it's a very interesting project because it's actually a global partnership, because the piers were designed and built in China, and then they transported, brought to here.
Is it the one that's like on the water and then goes up?
Exactly, right. There's a cable stayed bridge. Chinese are very advanced in design of cable stayed bridges because, in fact, the longest bridges in the world now, they're all in China, the top 5 or 6, and they're yet building 2 more bridges, one between mainland China and Hong Kong, and another one between Hong Kong and there's another island, I don't know if you've heard of it, Macau, which is part of China. So these are, I think the span is about like 2.8 kilometers long. Imagine 2 piers, 1 big deck, 2.8 kilometers long. And they're using all these new actually materials, composites. Even the cables are not steel. They're some kind of a carbon fiber or basalt fiber composites. But anyway, building bridges is really fascinating stuff. But long story short, they actually doing these, they do computational testing, and sometimes in this particular case, an experimental. The designer of that was a wonderful colleague, used to be the Dean of Engineering at UC San Diego. Frieder, I forgot his name. He was a professor there for a long time. And he's the one who built the Earthquake Engineering Center also at UC San Diego. Unfortunately, he left. He went to Monash University in Australia now. But anyway, so getting back to this. So we want to find the maximum displacement because we want to see if this would be safe. But the reason I actually give you this example is that sometimes intuitively we think that the dynamic load due to such a severe case of a blast loading would be something very serious. And what I'm going to show in this actual example is that as bad as it may sound, you may not even get to the point that the displacement would be close to even static displacement. So let's see that. So let's first calculate some of these parameters we need. We need to find the natural frequency, which is what? K over M. The weight is given. K is pound per inch divided by just the weight. So, or pound force divided by 386.4. So the natural frequency would be 34.05 radians per second. The period would be 2 pi over omega n, which is 0.1845, okay, seconds. So you can see that compared with the period of the system, natural period, is very, very small, okay. So obviously the response, and this is, of course, we assume, is undamped, because even undamped case is difficult enough to do these integrations. So is this, we need to evaluate, obviously, the response using Duhamel integral, and this is the general form, right? And the important part in evaluating the Duhamel integral is this forcing function which we need to formulate. And as you can see, we have 3 regions. For region 1, okay, f of tau is what? 2f0 over t naught times tau. Okay, this is for the case t greater than 0, less than t0 over 2. Okay, which is here. For case 2, f of tau is 2f0 times 1 minus tau over t0. So this is when t is greater than t0 over 2 and less than t naught. And for the third case, obviously, f of tau is 0. Okay. So let's do start with case 1. So for case 1, u of t is the integral 1 over m omega n integral from 0 to t. This is the part that you need to be careful. We are not evaluating this integral from 0 to t0 over 2, because we're not interested just in the particular value of the response at that point. We want to derive an expression for the response while the force acting on the system is that ramp loading going from 0 and later, before it gets to t0 over 2. So at any point of time. So if you do that, okay.
Professor?
Yes.
Why? Because I'm looking at the thing you sent us. It says f omega naught omega n t naught times t minus sine omega n t over omega n for the forcing
For
function.
the forcing function here, oh, I think this, because this is 2t0, this is t0.
Oh,
So I
okay.
gave t0 and t0 over 2.
Okay.
Right, the value of t0 was, in this case, instead of being t0, 2t0 is t0 and half of that.
Okay.
So that would be similar. Okay. So if you do that, you get, for the case 1, you have 2f0 over 2f0, right, over t0 tau, right, sine omega n t minus tau d tau. Obviously, I don't want to derive this. I just go to that table. If you go to that table, which is done by probably 2-3 pages of integration, you get u of t is equal to 2 after you simplify that, you get 2 of 0 over m omega n squared t naught t plus 1 over omega n sine, sine omega n, okay, t minus tau 0 to t, and you further simplify that for case 1, you get u of t being 2f0 over k t naught times t minus 1 over omega n sine omega n t. So this is for the case 1, okay? You can rewrite this by, in fact, factoring this out, because we always want to write dynamic response as a multiplier to the equivalent static response. So I can write that maybe this way also, 2 over t naught times t minus 1 over omega n sine omega n t. Okay.
Where's the math?
Oh, you know what happened? Here, omega n squared, I substitute that k over m. So m and m cancel out.
Omega n squared.
Yeah, we had omega n squared here, which is k
Oh.
over m.
Yeah.
So mass cancels out. Before I go any further to the other cases, I should point out an important observation that you can make also with Duhamel integral, or the response due to general loading. You always see that the response due to general loading depends on 2 important quantities. One is the natural frequency of the system, and the other one is the duration of the forcing function. So, in fact, as we will see later, we want to get a better understanding of how you develop an approach that can give you basically maximum response as a function of these two, which we'll get to that, shock spectrum. But make an observation here that the response is always a function of 2 important parameters. Depends on the natural frequency of the system as well as the time duration. Okay. So let's do it for the second case. For the second case, again, if you go to that table, you see that u of t can be derived this way, right? What happens here, basically, for the second case, you're talking about any time here, right? So the response would be accumulation of the response that you have gained all the way from here to here, which is governed by that, plus the response from this point on. So you have two integrals, one for evaluating the response from here to here. Now you have the particular value of t being t0/2. So you have the integral from 0 to t0/2 of 1/m⍵n of 2f0/t0 tau, okay, which is sine ⍵n t minus tau d tau, which is actually for the k for here to here, plus the integral 1/m⍵n from t0/2 all the way to any point of time of 2f0 times 1 minus tau over t0 sine ⍵n times t minus tau d tau. Again, as you can see, of course, this is quite involved, and using those tables, you see that this would become 2f0/k t0 times t0 minus t plus 1/⍵n times 2 sine ⍵n t minus t0/2 minus sine ⍵n t. Okay. So this is the response for the period when you have passed this peak and you're somewhere here. Okay. The third region is when that impulse loading has ended and you're beyond the point t0, or the system is now experiencing a free vibration, but that free vibration is due to the initial conditions that have been generated here, or in other words, U and U0 evaluated at that point from that expression. That's one way of doing it. Another approach would be, you can just simply write for the third period that U would be the integral, would be this, m⍵n of 2f0 tau sine ⍵n t minus tau d tau, the integral from 0 to t0/2, total response from here to here, plus the integral m⍵n t0/2 to t0 of 2f0 times 1 minus tau over t0 of sine ⍵n t minus tau d tau, which is from here to here, plus 1/m⍵n from t0 to t of f of tau sine ⍵n t minus tau d tau, where f of t is from here on, which is obviously 0. So the response from this point on would be just summation of these two, that if you simplify that, you get 2f0/k t0 ⍵n times 2 sine ⍵n t minus t0/2 minus sine ⍵n t minus sine omega n t minus t naught. Okay. Okay. So this is for the third region. As I said, in the case of Duhamel integral or general loading though, the challenge is you do not know where the maximum displacement is going to be. Is your system going to experience its maximum displacement when the force is acting in this region, or here, or afterward? Intuitively, you would naturally assume that in fact, the maximum displacement would be when the force is acting on the system. Let's confirm that, or let's verify that. So the only way we can do that is that for each case, taking the derivative of u, equate that to 0, find the t at which that is maximum, substitute back into that equation, find that u for each of these cases, repeating the same approach to see which one is the maximum. So let's do that. So what I'm going to do is, first, let's take the derivative of that first function. If you look at the first function, evaluate du dt, you will see that would become 2f0 over k t0 times 1 minus cosine omega n t. Okay. Let me write all of them. For 2, du dt would be 2f0 over k t0 times -1 plus 2 cosine omega n t minus t0 over 2 minus cosine omega n t. And for the third, minus cosine omega n times t minus t0. So these are the three derivatives. Obviously, you need to equate these to 0, find those times from each, substitute it back into the corresponding equation to find which one is maximum. However, the good news is you don't have to necessarily do that. Go through that cumbersome, the function, okay? I look at this and I look at the time duration, right? From here to here, the only part that is function of time is this, that can change as time goes from 0 to 0.0155, right? At the most, that cosine would be the cosine of 0.0155, which is a small positive number. What does that tell you? That means throughout this whole period, this derivative, this is a positive value, right? And this is a positive value. So during this phase, this derivative will always be greater than 0, cannot be 0. That means you have a function that is derivative is always positive. So no maximum can be reached during that period because function has a positive, in other words, if you even just plot that, right, is as if something like this. You have a curve like this. Has a positive slope all the way. Is never reaching yet to a maximum value. Continues even up to this point, the derivative is positive. So it hasn't reached a maximum. So I would rule that out. That in this region, you cannot reach a maximum value. So while the force is acting from here to here, in this ramp loading, maximum value is not possible. Continue, because it's still, response is increasing, continues to increase, right? In the second case, okay, let's evaluate this. For instance, at t equal to that t, I mean, basically substituting for t, as t is increasing from 0.0115 all the way getting to here. Let's say evaluate it at this point, right? Because you see t is t minus t0 over naught is always positive, right? Is going to be always positive. And this is positive, but small value. But let me put those in. If you do that, let's say you have 2f0 over k t0 times -1 plus 2 cosine of, if you put for omega n and t minus t0, which is at t0, you get 0.5108 minus cosine of 1 minus, I'm sorry, 1.0216, which becomes, okay, actually would be this, becomes 2f0 over k times 0.227, which is positive. So the slope, or the value, the derivative, stays positive, again, throughout this whole region. In other words, if you think of that function, this function is continuing to have experience a positive slope that is increasing. It's not reaching a peak. So we conclude then that if there is going to be a maximum value for the u, has to happen or take place during this region, or in other words, from here. So what I will do, I would evaluate that, okay? What I will do, I will evaluate t, put it back into that equation, okay? And find out the maximum value. So the equation that I erased it, right? I may need to write it down. U of t was 2f0 over k t0 omega n times 2 sine of omega n t minus t0 minus sine omega n t minus sine omega n t minus t0, okay? I want to find, set this equal to 0, find t, put it into this equation. As you can see, of course, is not easy. So we do a little bit of mathematical manipulation. What I will do, I will expand this so that I have just sine of omega n t and cosine of omega n t0. If you expand that, in other words, if you expand this, what you get is this: 2 sine omega n t cosine omega n t0 over 2 minus 2 cosine omega n t sine omega n T0 over 2 minus sine omega n t minus sine omega n t cosine omega n T0 plus cosine omega n t sine omega n T0. This can be simplified to sine omega n t times 2 cosine of, I would substitute, of course, for the T0, so it would be 0.5108 minus 1 minus cosine of 1.0216. So in other words, if I do that, and I can send this to you, you'll get a function that looks like this. Maybe I would stop here because I don't want to just rush through it. We will derive basically the value for the u for this case and find out the maximum displacement. So why don't I stop right here? We'll finish it next time.